And so we introduced to our study of dynamics and kinematics the concept of rotation. Previously we have only been dealing with translational motion. And I remind you that yet a third possibility is vibrational motion, that with translational motion the objects change their position, they go from one place to another, whereas in rotation they do not change their position. At least the axis of the rotating object does not change its position. Instead, they change their orientation. They change the angle that they are at. So let's look at this picture. That the various points, the South American continent, would be translating, moving in a circle. But if you consider the world as a whole, then it is not, if we're only considering its rotation and not its orbiting about the sun, that as it spins, the axis here is not what we're focusing on as translating, what is happening is it is turning through an angle that South America is coming to be at a new orientation, but that the Earth itself is not moving. That the angle that you turn through is going to be the same for all parts of this rotating object. That there is a value, that is the amount of rotation that has occurred. With the concept of translation, we have all of these quantities that we have analyzed very carefully, and each of them has a rotational analog, that instead of position and then change in position, which we call displacement, now we will have orientation. The angle at which you are facing, and then the change in the angle, and that is angular displacement. Again, the rate of change in position, or the rate of change in angular position, is known as the average angular velocity, just as it was the case in the translational instance. We used the letter omega. That is not a W. Please don't make it look like a W. Make sure it's nice and pretty and curly. Going from average to instantaneous was a matter of letting this interval of time become infinitesimally small, and the same works here. Instead of this large change in position, if we do a little infinitesimal change in angular position, which happens in an infinitesimal amount of time, that rate is what we call the instantaneous angular velocity. And then similarly, if to what we did translationally, if you do the change in angular velocity with respect to change in time, that is the average angular acceleration. We used an alpha for that, and in the instantaneous rate of change would be the instantaneous angular acceleration. So you were going from these Latin letters to Greek letters. Sometimes that freaks people out. Try not to let it. It's the same ideas you dealt with before over in this case. You need to remember that the definition of an angle in radians, and we will be working with radians when we are dealing with rotational motion and not degrees, that the angle in radians is equal to the arc mapped out by that change, this arc here, divided by the radius. And that would be the angle in radians. That this is a much smaller path, but it's a smaller radius to there. And if you do that division, then you do get the same angle that it has turned through. Well, if we then take this expression and take the derivative of it with respect to time to get to here, then the derivative of theta with respect to time is going to be omega, and the derivative of this distance, this arc, with respect to time is going to be the velocity. R is a constant, and so when you take the derivative of it with respect to time, it's a zero. So it's really a variable divided by a constant, and so it's the derivative of the variable divided by that constant. Again, if you take the derivative of this expression with respect to time, here you get acceleration, and the derivative of velocity with respect to time is the translational acceleration. But note I put a little t there. What do you think that t stands for? And it's not time, it is tangential. That if I write this expression again, I could multiply through by r. The tangential acceleration is equal to alpha times r, but there's another acceleration. The radial acceleration, not the acceleration tangent to the circle, but the acceleration radial along the line going in towards the center of the circle, also known as the centripetal acceleration, which you recall is equal to v squared over r. But then if I replace v by omega times r, you can see that this becomes omega squared r. So there is an expression for centripetal acceleration in the rotational case. Be very careful to remember that there are two accelerations possible for an object going in a circle. This one is necessary if you're going in a circle. This one is optional. You might be going in uniform circular motion, in which case the tangential acceleration would be zero. These quantities that we have just introduced are vectors. Well, that's not true. I'm spoiling my surprise, but most of them are vectors, and their direction is given by a right-hand convention. That if this disk is rotating as indicated by this arrow, you take your right hand and get your fingers to wrap in the direction this is going, and your thumb then points in the direction of these vectors. So this has an omega that is going down, this disk turning in this way. If perhaps it was slowing, it was turning in this direction but going slower and slower, then it would have an angular acceleration that was going up, because the change in omega would be this way, and you would turn your right hand over so that your fingers wrapped in that way contrary to this current arrow. That would cause your thumb to point up. Okay, I hope that works for you. It's pretty important. Direction of these vector quantities. But you may or may not recall, way back at the beginning of the year, we did a little exercise with a book. And we had two angular displacements, two delta thetas. We had a 90-degree angular displacement, and in this case we're starting with the angular displacement around an axis that goes as the type is written across the page. That 90-degree turn causes this book to change from having its front to having its back, and I bet I messed up. And then we did a 90-degree turn around the what do you call this? The axis of symmetry, a line going through the face of the book, and that turn of 90 turns this book around so it stands up like that with its back facing you. If you do those two turns in the opposite order, we start with, this started with a turn about the line going up as the type went. This time we're doing the line, okay, we're doing a turn along the spine of the book around that direction. Was this second turn around the spine? The spine axis. Spine axis. Turn around. I don't know. At any rate, what this is supposed to be, and suddenly Mr. Houghton is confused, is the same two turns, 90 degrees around an axis that goes that way, and that gets this book to here, boom, and then 90 degrees around an axis that goes up and down. Yeah, it's a mistake to talk about it in terms of the book. An axis that goes off in the Z direction and an axis that goes in the J direction. Okay. The point that was made long ago, don't rush me, I'm getting there, is that the results of the addition of those two delta thetas is not the same. Therefore, delta theta was not a commutative operation, and not being commutative means delta theta is not a vector. So this here is not a vector quantity, though delta x is, because this is not commutative in its addition. Oh my. Does that mean that everything else cannot be vectors because they are built out of this? And the answer is no. That delta theta is not a vector, so delta theta divided by delta t would not be a vector. Average angular velocity is not a vector, but instantaneous angular velocity is equal to d theta dt. And if you do the same thing, you turn around an axis, and I really screwed up this picture because I didn't know what was going on, but if you turn around an axis that's going vertically or an axis that's going off in the z direction, a very small amount, and then do the other operation, a very small amount, an infinitesimal change in theta, the results do come out apparently very, very similar, and I believe that if you made delta theta small enough, they would come out identical. So when you do a gross change, a delta x, then the addition is not commutative. But when you do a subtle change, a d theta, I said x, a d theta, then it does come out to be commutative. Hallelujah. So while delta theta is not a vector, d theta is. So omega is a vector. Now, average angular acceleration would be a vector quantity because this is a change in the instantaneous omegas, and they are vectors. So the difference in those would also be a vector. So this is a vector, and this is a vector. So these three quantities are vectors. These three quantities are not, because of the failure to have commutative addition. I think that's kind of cool, and I wish I had my act together better. Here you have, and I'm sorry for the poor fuzzy quality of this, but here are the equations of dynamics that you worked with in the translational case, and here are their rotational analogs that we will be working with in this unit. And you can see that it's just a matter of replacing x's by thetas, v's by omegas, and a's by alphas, and exactly the same equation. So that should be very nice. And you will recall that the other detail is that I can only use these equations, and the people fill in the blank with a loud amen preceded by constant angular acceleration. And so when you use one of these equations, any one of these equations, you will always follow that statement by the fact that delta alpha equals 0. And there will be cases where delta alpha is not 0. And so don't just write that because it's busy work, Mr. Houghton asks. Write that as a chance to reflect. Is delta alpha really 0? And if it's not, you can't use the equation. Probably you will do it in terms of energy in that case. Here we have a checkpoint, and just for your whatever reason Mr. Houghton might have, wink wink, I put up those 5 dynamics equations again, but go ahead and do this checkpoint. It should be very easy. This checkpoint has 2 parts. In the first part, we've combined A and B together so that does it have radial acceleration, does it have tangential acceleration, and you can say it has both, or it has neither, or one and not the other. And then the second part was part C of this checkpoint, and there we'll put C and D together. So you'll do that. And that concludes today's event.